Today, I plan to convince you that you should stop representing your file paths as strings and start using pathlib. First, a quick additional introduction. I hope folks level up their Python skills. I run both virtual and on-site Python workshops and courses for teams. And I run Python Morsels, which is a weekly skill-building service for Python developers of all skill levels. I also share a Python tip every week through my newsletter, which you can find at trey.io/news. Now let's talk about file paths. For most of Python's history, file paths have been represented as strings. This still works today, and it always will. But there are problems with representing file paths as strings, which is why about 10 years ago, the Python core developers introduced pathlib. There are 4 reasons that I recommend using pathlib. 2 of them are about the various utilities that pathlib competes with, and 2 of them are about the problem with representing file paths as strings. The alternatives to pathlib are difficult to find and difficult to use. Also, representing file paths as strings requires deliberate effort to avoid writing buggy code. And path strings make it harder to distinguish between a path and any other string in your code. So I'd like to address each of these before we talk about pathlib itself. So let's hop in a time machine and roll back the clock about 10 years. The year is 2015. The Late Show with Stephen Colbert has just premiered. TikTok didn't exist yet, but there was something called Vine. And everyone was arguing about whether the dress was black and blue or white and gold. Also, everyone was preparing their Left Shark Halloween costumes. And most of the Python community, myself included, were still using Python 2.7, which won't be end-of-lifed for another 5 years. So that's where we're at right now. At that time, when you needed to work with file paths, there were 4 standard library modules that we might reach for: OS, os.path, glob, and shutil. shutil has a bunch of high-level file-related stuff, including 7 different functions for copying files and directories. The glob module is a lot simpler. It has glob, iglob, and 2 other functions. The os.path module is for manipulating file paths, splitting paths apart, joining them together, and generally asking questions of path strings. The OS module is a bit more complicated. The Python standard library has 2 modules that act as junk drawers: the OS module and the sys module. The sys module is the junk drawer for stuff related to the Python interpreter. The OS module is the junk drawer for stuff related to the computer that your code is running on. The OS module has lots of file-related stuff and a bunch of not-so-file-related stuff. There are utilities for getting the current working directory and for changing directories, for changing the mode of a file, stuff for working with symbolic links and hard links, utilities for traversing the file system, utilities for renaming and replacing files, and utilities for making directories. These are most of the file-related utilities in Python's OS module. But this is not everything in Python's OS module. There's also all of this. And this. Also this. And this. And this too. And this. Plus this. That's everything in the OS module. Well, that's all the functions in the OS module. There are also dozens of constants that I'm not going to show you. Now, my point in dumping out the OS junk drawer is to point out how difficult it can be to find the dozen-ish path-related utilities that are in the OS module. And these are just the ones that live in the OS module. This doesn't include everything in os.path, shutil, and glob. These are most of the path-related utilities included in the Python standard library. I removed about 10 from this slide. Back in 2015, in Python 2.7, our only option when working with file paths was to go hunting for these utilities when we needed them. So, I think we can all agree at this point that the various path-related utilities scattered throughout the Python standard library are difficult to find. But do we even need these utility functions? If we're representing file paths as strings, couldn't we just manipulate the strings with string operations? This code was taken from a Django project. It sets base dir to the directory above the current above the current files directory. And it sets templates dir to the templates subdirectory within that base directory. But these file paths are just strings. So instead of os.path.dir_name and os.path.join, couldn't we just use the string rsplit method in string concatenation? This code is shorter, but it's probably buggy on Windows, which usually uses backslashes instead of forward slashes. Now, we could have relied on os.sep to make this code work on all operating systems, but I think this code is less readable than the os.path version that we started with. Also, depending on where our path came from, we might accidentally end up with a mix of forward slashes and backslashes, which is technically valid on Windows, but it also looks really weird. Which is why the many os.path utilities are useful, but performing string manipulations on path strings is tempting, and it can get us into trouble. If we forget to use these utilities and instead we perform string manipulations on our path strings directly, we might end up with buggy code. So, using strings to represent paths can easily lead to bugs unless we're very careful to use the proper path manipulation tools. But potential bugs aren't the only issue with representing paths as strings. Stringly typed code is code that passes around strings when a better type exists. This is stringly typed code. It uses a string to represent a date. This code uses the datetime module to represent a date instead. I prefer this second block of code. It's a bit easier to work with date objects than it is to work with strings. And we automatically get a bit more certainty about whether our data might be invalid. As we've discussed, old Python code always used strings to represent file paths. I would argue that this is stringly typed code. There is a better way to write this code, using the path class from Python's pathlib module, which we'll talk about a little bit more later. But first I'd like to acknowledge the fact that using path objects instead of strings makes it easier to distinguish between file names and any other string in our code. If your code uses type annotations, a file path might look just like any other string, which can make it harder to catch path-related bugs, and it can make it harder to reason about your code. So, we've seen that the alternatives to pathlib are difficult to find, that path strings are error-prone, and that path strings also make it difficult to distinguish between paths and non-path strings. I'd like to quickly address my last point by comparison to pathlib. Let's compare the readability of code that represents paths as strings to the same code that uses pathlib.Path objects. So this code represents paths as strings. We just saw it. I find that I need to read this code inside out. We get the absolute path, and then we get the parent directory, and then we get its parent directory. Instead of this code, if we use the pathlib version, we can read this from left to right. We resolve the path into an absolute path, then we get the parent directory, and then we get its parent directory. When using path strings, we need to use nested function calls. But when we use path objects, we can use chained method calls and attribute accesses. Personally, I think the pathlib version reads more naturally. Here's another example comparing the glob module and pathlib. Instead of joining a path and then passing it to iglob, with pathlib, we just call the rglob method on that path. Shorter code isn't always more readable, but when the shorter code is less noisy, it usually is. I very often need to open a file, read the whole contents of the file into a string, and then close the file. With pathlib, there's a convenience method for that. Instead of using the open function, we can just call the read text method on a path object. The methods on the pathlib.Path class are a bit more deliberately designed than many of the other path-related functions that have been added to Python over the years. If you wanted to make a directory before pathlib, you would either use os.mkdir or os.makeDirs, depending on whether you wanted to make parent directories as well. With path objects, the mkdir method includes the ability to make missing parent directories thanks to the optional parents keyword argument. Copying files is another good example of where pathlib shines. In Python 3.14, which will be released next month hopefully, pathlib's path class will have a copy method and a copy into method. Before these two methods existed, we needed to reach for either copy file, copy, copy to, or copy tree. All of these have slightly different uses, and I always need to read the documentation to figure out which one I actually want. So, code that uses pathlib is often more readable than the alternative. But how does pathlib actually work? Well, the pathlib module contains pretty much one thing, a class called path. So understanding pathlib means understanding path objects and the path class. The path class accepts a string, which represents a file, and returns a new path object. The path object that we get is either a POSIX path or Windows path, depending on the operating system that our code is running on. Now, both types support all the same features, but they normalize paths differently. We don't need to worry about any of that, though, because the path object that we get should pretty much just work the way we'd expect it to on whatever operating system our code happens to be running on at that time. This is pretty much everything that's in that path class that I find useful. Most of these are methods that you can call on individual path objects. Some of these are attributes on path objects, and two of these are class methods. One returns the current working directory, the other one the user's home directory. Technically, these are only about half of the 70-ish methods and attributes that are on path objects. These are the rest of those, but I don't find myself using these ones quite so much. So path objects have lots of useful features built in, but what happens when you actually want to use a path object as a file path? Back when pathlib was first added to Python, in order to actually use a path object, you might have to convert that path to a string. Today, fortunately, that's completely unnecessary, because Python's built-in open function accepts path objects. The open function used to only accept strings, but since Python 3.6, open works with strings or pathlib.Path objects. In fact, pretty much every utility in Python that accepts a file path as a string will also accept a path object. Whether you need to change directories, change the ownership of a file, connect to a SQLite database, log to a file, create a zip file, or run a subprocess, you can use pathlib.Path objects instead of using path strings. You don't need to convert path objects back into strings in order to use them. Every standard library function that should accept path objects does. In fact, even standard library functions that are specifically designed to work with path strings will also work with path objects. If you're still using os.path, that's okay. All of these functions also accept pathlib.Path objects. They'll give you a string back, but they will accept a path object. Every path-related utility that we saw earlier that accepts a file path will also accept a pathlib.Path object. So you can usually pass path objects to legacy code that was written without pathlib in mind, and it often just works. Even most third-party libraries that handle file paths will usually accept pathlib.Path objects. Django, Pandas, Pillow, PyTest, and Click all support path objects. Most modern Python libraries work just fine with pathlib. So pathlib is great, but in practice, how should you start using it in your own code? Pretty much anytime you encounter a string that represents a file path, you'll usually pass that string to the path class and get a path object back. When you're writing cross-platform compatible code, you want to use forward slashes in the string literals that you pass to pathlib.Path, but don't worry about backslashes on Windows. If you end up with a backslash separated path on a Windows machine, it'll normalize it. On Windows, this path that has a backslash separator will be interpreted the same way as this other equivalent path that uses forward slashes. They mean the same thing. Once you have a path object, there are lots of things that you can do with it. If your path object represents a directory, you may end up joining your path with a file name. You could do that with the join path method, or using the slash operator, which looked a little bit weird to me at first, but now that I'm used to it, I find it pretty readable. Also, the path class can accept multiple arguments to join together, and those arguments can be either strings or path objects. So this joins our home directory path with this config file name. All three of these approaches are equivalent. They make the same path object. And none of these is necessarily better than the others, though that third one you don't usually see unless you're unsure whether the path you're working with is a string or it's already a path object. I always found the functions in os.path to be unfortunately named. Lots of words, shortened words, all squashed together. With pathlib, all the same functionality exists is either methods or attributes on path objects, and they're pretty well named. Personally, I prefer the name attribute over the base name function, the parent attribute over the dir name function, and the suffix attribute over calling split ext and accessing index 1. If you're looking for a pathlib cheat sheet, take a look at these two URLs. The first URL there is an article I've written that has a couple different cheat sheets in it. The second one goes to the pathlib documentation, specifically the bottom of the page, which compares pathlib to os.path and a couple other things in the standard library. Now, this talk is about pathlib, but it isn't just about pathlib. Code that uses pathlib can also work with code that inherits from pathlib.Path objects, and it's also possible to practice duck typing when it comes to path objects. Since Python 3.12, you can extend the functionality of pathlib through inheritance. So if you'd like to make your own path objects that include a method to change directories, you can. You inherit from pathlib.Path, and then you use your own custom better path class the same way you'd use the pathlib.Path class, and it just works. Inheriting from path class, the path class probably isn't something that you'll do very often, but when you do, also keep in mind there's other goodies that you should look into. For example, if you need to attach metadata to a path class, to a path object rather, you can override the with segments method. This will ensure that the metadata is preserved for all new paths that are derived from an existing path. So for example, if we get the parent directory of one of these custom git path objects, our repo root attribute will be maintained on the new git path object that's returned. And again, you're probably not going to be inheriting from pathlib.Path very often, but know that you can if you want to. So you can make a sort of pathlib alternative by making specialized subclasses of pathlib.Path. But you can also make pathlib alternatives through duck typing. An object that acts like a list or a tuple is a sequence. An object that acts like a dictionary is a mapping. And an object that acts like a file is a file-like object. An object that can be used anywhere a path object can be used is a path-like object. If it looks like a duck and quacks like a duck, it's a duck. And if it's accepted by utilities that accept path objects, then it's a path object, or at least a path-like object. PEP 519 defines the path-like protocol. All path-like objects are accepted by open and all other built-in path tools. The only thing that's needed for a path-like object is a dunder_fs_path method. That one method will allow an object to be accepted by all of Python's many path-related utilities. And any third-party utility that wants to convert a path-like object back into a string can use os.fs_path to do that officially. This PEP allows for a whole ecosystem of path-related or path-like objects beyond just pathlib itself, and they'll just work with everything that's built into Python that's meant to work with paths. For example, here's a class called myPath that does not inherit from pathlib.Path, and yet instances of this class work with the built-in open function. The ability to make an object that acts like a path allows for third-party libraries that work everywhere that pathlib works. So if you don't like the way pathlib works, you can invent your own pathlib and it just works with all the stuff built into Python. Now, before we conclude, I'd like to make sure to discuss a couple common mistakes that new pathlib users often make. The path class has an open method. Back in Python 3.5, the open method was the official way to get an open file out of a path object. The path-like interface was added in Python 3.6, thanks to PEP 519, as we just saw. So now path objects work with the built-in open function. There is no reason to use the open method anymore. The open method only exists because there were two versions of Python that included pathlib before the open function worked with pathlib. So I recommend against using the open method. I consider the open method to be a relic from an earlier version of Python. If I need to display a path to an end user or log it to a file, I often implicitly convert it to a string by using a print call or an fstring. And that's useful. But don't convert path objects to strings when you don't need to. If you think you need to convert a path object to a string, you probably don't. Also, don't forget that the path constructor can accept multiple arguments. So, if you have a directory string, that is, and a file string, and you'd like to join them together, you don't need to make a path object and then use the join path method or the slash operator. You can just pass both of those strings to the path class directly. This even works if you're not sure whether one of those is already a path object or whether it's still a string. So with pathlib, it's easy to write code that works on all operating systems. Many common operations are made even simpler than they were before, and you get to avoid awkward stringly typed code. Pathlib can help make your code more readable and more maintainable, but there is a very common concern that I often hear about pathlib that I feel is slightly unwarranted. Pathlib is slow. It is true that pathlib can be slower for some operations, but readability is sometimes worth a small performance penalty. I searched 400,000 files with os.walk and with the pathlib walk method, and pathlib wasn't any slower. Except the walk method returns strings on path objects, which is a bit of a cheat. It doesn't actually return path objects themselves. So when I converted all of those 400,000 paths back into path objects in order to ask questions of them, my code did slow down. Although, unless I'm actually planning to process many thousands of files, this kind of slowdown probably isn't very significant. Most path operations aren't in tight loops. Readability is usually more important than micro-optimizations. Use the right tool for the right job. Optimize only when it really matters. Pathlib isn't just a different API. Pathlib is about acknowledging that file paths are important enough to warrant their own data type. A data type that's designed to make file path operations easy. It's about representing file paths properly. Thank you.